All right, so last time what we did was to generalize the superposition principle to continuous charge distribution, right? So to calculate the electric field created by continuous charge distribution, and what you need to do is just you're going to replace the summation with an integral, okay? So you just use a different mathematical tool, the calculus, instead of algebra to calculate the electric field, right? So usually you can use some symmetry to reduce this integral to a scalar integral, right? Because we still need to add all these e's together, little e's together, but if you have an infinite number of elements, this becomes an integral, right? And then the infinitesimal element, we call it dE, okay? So, and this is going to be a vector integral. Look at this, everything is vector. So you need to do that in x and y directions, okay? And this problem we did last time, we figured that y components cancel because of the symmetry in this problem, right? All the y components cancel because we are only looking at a point on the axis crossing the center of the rod. So the y components cancel. So we only calculated the x components. But in order to calculate x components, we started with the fundamental theory. The fundamental theory is still this, right? The electric field from any point charge is this theory, okay? But now you pick an infinitesimal charge, you call it dq, okay? You can still use this theory, so the electric field becomes dE equals this ke dq over r squared, right? And then in order to find the x components, we still did vector analysis, but everything symbols, okay? So, and the end, our goal is to reduce the integral to one variable, right? We started with the integral with a few variables. Our goal was to reduce the integral to one variable, one function, and then we can look up an integral table, look it up in the integral table, and then use the upper and lower bounds to evaluate this integral, so to find our final answer. This was our final answer, okay? And then this is actually, as I said, this is one of the hardest part in this class because this is totally different from algebra, right? Totally different from algebra, okay? Okay, so that's what we learned last time. Now we're gonna practice. Of course, as I said, it's only true if I'm looking for the electric field at a point along this axis, right? Say if I want to find the electric field at this point, of course all y components are not going to cancel, right? But you can still do that, right? All you need to do is just you just calculate this, which is dx. You just repeat the same process, okay, with the x component, y components, right? In order to find this expression, you use that, you do vector analysis, cosine, sine, right? You do the same thing, y component. The only thing that changes is going to be the y component, right? So pretty much it's just going to repeat the same process for x and y. So in principle, you can actually calculate the electric field at any point, okay, I pick around this rod. So again, you see, using that theory, I can find out the electric field at any point. So I'm done with this rod. Okay, I'm done with this one-dimensional rod. I can find, in principle, I can find the electric field at any point created by this rod, still using this theory, but with a more powerful mathematical tool, calculus. Okay, so that's the idea. Now we're going to do another example. It's still one-dimensional, but it's not a straight. Okay, it's a circle. Okay, it's a ring. Okay, so let's take still the same PowerPoint, slide 6. So, before that, let's see. There's another very useful conclusion, okay, about this, is that when you apply this conclusion to a very, very long rod, okay, so the rod is very long, like 10 meters, okay, and compared to the distance D from the point, right? So even if like the rod is not very long, it's like this, but I'm only interested in the electric field at a point like this close to it. So this D, this is the D, very small, okay? So if I take this limit, the length of the rod is much, much bigger than the distance. So I'm only interested in either the rod is very long, or I'm interested in a point very, very close to the rod, okay? So this is actually going to be reduced to an even simpler, okay, expression. Because if this L is much, much greater than D, then this thing, it's going to be almost, let's see. So that means compared to L, D is going to be very, very small, right? So that means if you add D squared to this squared, it's going to be almost the 1/2 L squared, right? Remember, this is going to be very small compared to this. So you would just get big Q at the top, little d still there, and then you get a 1/2 L squared and the square root. Well, that's just going to give you 1/2 L, right? So you finish the algebra, at the end you will get this. Ke times 2Q over D times L. Okay? And then if the rod is very, very long, right? Very, very long, but this Q over L is still a uniform charge, it's going to become the lambda E we define, right? So all I need to know is actually the lambda E, the linear charge density. I don't even need to know the total charge and total length, right? So this is going to become a very easy, simple expression, okay? So it all totally depends on, only depends on the distance from the rod and the linear charge density, okay? It doesn't depend on the Q and L, right? So it's even simpler than that. So that's one conclusion when the rod is very, very long, okay? Again, you don't need to memorize this, okay? You never need to remember these shortcuts, these conclusions we drew, okay? And then you just plug numbers in, right? All right, so this is the rod, we're done with the rod. So next thing we're gonna do is this, this ring, okay? So let's take a look at this ring. All right, so this guy say I have a very thin ring, okay? So this ring has been charged with a lot of positive charge, uniformly charged, okay? And then I want to find the electric field, again, let's make it simple, on the axis crossing the center of this ring, okay? So it's still P, and the distance from the ring to this is going to be D, okay? So this looks more difficult than the rod, but actually turns out the math, it's actually easier. Okay, you don't even need to use the integral table. We're going to still start with the integral, but at the end you don't even need to look it up. The integral is much, much easier because you're not going to get any function in the integral. Okay, so let's see. But the theory is still the same, right? We're still practicing the theory. That's why we do we practice. Okay, in order to just we apply the same theory to different problem. That's what we learn in physics. So, okay, what is the theory? The theory is this, right? I'm going to still pick a very, very small infinitesimal charge, infinitely small charge on this ring, and then draw the electric field, right? And then from the what I learned in the previous one, okay, use the symmetry of the ring to see if you can find another charge, right, which can cancel some components to help us make the calculations a little bit easier. Even if we cannot cancel any components, even there's no symmetry we can use, that's fine. I'm just going to do that in X and Y components, right? Repeat the same process. Now let's see. Say I pick this guy, right at the top. How do you draw the electric field? Okay, well, the electric field is going to be this, right? Connect these two lines, and then the if this is positive, the electric field is going to be in that direction. Okay, if I call this E1, and this is Q1, and then I'm going to pick the same amount of charge at the bottom, right? because I already learned that from the previous one, so I have some experience. That's why we practice, right? You do need to practice, so you have some experience. You learn some tricks. So next time you see a similar problem, you know how what to do. Okay, that's the reason we practice. You never know this before you practice. Okay. Now pick this one, and what is the electric field? Well, connect these 2 points. Now the electric field is going to be in that direction. All right, okay, looks familiar, right? We have done this before. E1 and E2, because I'm going to make sure that I pick like, you know, 0.0001 coulomb here, 0.0001 coulomb down here. So these two electric fields, the magnitudes are going to be the same, right? E1 is going to be equal, to E2, and then because I picked this one right at the top, this one right at the bottom, so these two right triangles, they're going to be identical, right? So the hypotenuse the same, the angle is going to be the same, right? Whatever you call it. So if you break these two electric fields into X and Y, so again, Y components are canceled, right? These vertical components cancel. Only X components are left, right? So E2Y, E1Y, they're going to cancel, right? So only the X components are left, and all the X components, they're going to add, right? And you can just literally add them because they are in the same direction. Okay, so okay, from the symmetry, I know that I only need to find the X component, right? I don't need to, it makes my calculations easier, okay, using the symmetry. So I still know that the electric field only has an X component, right? No Y component, all right? Now, how do I find the X component? Okay, now because we have done a problem last time, so this time I have some experience, so I can do it a little bit faster. Okay, that's the idea. That's why we practice. So this guy, you see, the steps are still the same, right? Up to now, it's gonna be dx, right? The same, no change, no change. Okay, because the theory is the same, and then the symmetry also helps us get rid of these Y components. Now, and what about this guy? Okay, this dEx using this diagram is still going to be the same. It's going to be dE times cosine theta, right? So now let's get rid of this. I'm going to do that here. All right, so the steps are still the same up to now because we're still using the same theory. And then Y components still cancel, X components are still cosine, and this question, right? So now I know that all I need to do is just pick a dq. So I know that all these Y components are going to be canceled, right? So all these charges is charged. Okay, so if I want to find this guy, the electric field at this point, I know that the electric field only is in that direction. All I need to do is just pick a dq. Okay, because I know that the Y component of this guy is going to be canceled by this guy, right? Okay, so what about this guy? This guy is going to be canceled by this guy. Well, think about it, right? So they're going to make make an angle, okay? So their triangles is not like on this plane, but still the vertical components are going to cancel, okay, for these two guys, okay? If you pick this guy, you're going to find another charge here. They are going to cancel the vertical components, right? So remember, imagine the ring is in this direction on this plane, okay? Or if you just rotate this a little bit, so this becomes the top, this becomes the bottom, right? So using the symmetry, all these components perpendicular to this axis are going to cancel out. So you actually have a lot of components in all directions, but they're going to cancel out, right? So still, I'm left with Y component. Okay? So now I'm just going to focus on dq. Let's call this guy dq. So if I call this guy dq, so let's repeat the same process, right? This guy creates an electric field in that direction. I can call it dE, right? And if this angle is theta, well, theta or F or whatever you call it. So the steps are still the same, right? The net electric field in x direction is going to be dx. You add them together, now you have an infinite number of a dE, infinite number of the electric fields. You're going to just integrate that. And this becomes dE cosine theta, right? And then, okay, how do you calculate dE? I can still use the same theory. Nothing has changed. Ke dq over r squared. This is dE. All right. How do you calculate cosine theta? Well, I can still calculate cosine theta in this right triangle. Okay. So in this right triangle, cosine theta is going to be the distance d over r. Right. Nothing has changed. Okay. Nothing has changed. Okay, and remember what we did last time? Okay, first of all, I can take out this Ke and D. Let's get rid of some constants. And then I can put dq over r cubed together. Nothing has changed, right? If you compare the steps with the last lecture, nothing has changed so far, okay? Now things are going to change because remember what we did is that, okay, we wrote dq and then r, okay, both as the function of y in the rod problem, right? And then everything becomes a function of y. So this integral becomes one variable, so you can evaluate that using the integral table. But in this problem, it's actually even easier, okay? Because you can realize that, how do I find this r? Well, the r, okay, easy. That's going to be d squared, which is this side plus this side. And this side is the radius of this ring, right? Let's call it a big R, okay? And this big R turns out to be a constant, right? So if you pick this point, it's going to be a right triangle in that direction, but this side is still R, okay? Should you imagine you're going to get the right triangle in 3 dimensions, okay? So actually, for all this dq you pick, remember, what you're going to do is that you're going to integrate the dq, the E, along this ring. But for every dq you pick, right, if you pick this dq, you're going to have a right triangle this way. This is the side, one side, this is the side, and then this is the hypotenuse, right? So you always have D and R, D and R, D and R, D and R, okay? You always get the same right triangle. So you always have this little r as d squared plus this radius squared. So which is going to be a constant in this problem, right? Because you don't have any charge here, here, or here, right? If you have charges here, then the distance is going to change, right? So you get different right triangles, right? But you don't, so this is not the rod problem, right? I only have the charges along the ring, and they always make the same right triangle with this side and this hypotenuse. So this little, the distance from every dq to this point P is a constant in this problem. So it makes my life even easier than the rod, right? Even though this seems like, okay, more difficult than the rod, it's a ring. But the algebra, the math is actually easier, okay? All right? So this R, I can also take it out. So now things are changing, right? And it's actually becoming easier. So this R, I can write it as d squared plus r squared 3/2, right? And this is not y anymore because I don't have any variable in this distance. The distance little r is a constant in this problem. Then I only need to integrate dq. Now again, we can use the linear charge density to evaluate this dq, right? Because remember, if you pick a dq, right, this guy is going to have a very, very small length, okay? So now we're not going to call it dx or dy because it's not like, you know, you're going to pick it's an arc, right? You're going to pick a very, very small length on this ring, okay? So again, use whatever symbol you like. Let's just use dl, okay? Because it's a very small length, and let's use dl. So this dq, obviously it's gonna be, if I want you to find the dq for a very, very small segment I pick on this ring, you would do total charge divided by the total length of the ring, and then times the very, very small length of the small segment I pick, right? So again, as I said, imagine this guy has a charge like 2 coulombs, the length is like 5 meters, right? And then I want you to find the charge on a 0.0001 meter segment. What are you going to do? Well, you would say the charge is just going to be 2 coulombs divided by 5 meters times 0.0001 meter. Right? If I pick a very, very small segment, I say the length is only this. Tell me the charge on that little piece. That's what you're going to do, right? Divide the total charge by the total length and then multiply by the segment I pick. Now we're just using symbols, right? Still total charge divided by total length times this dl. Okay? Now, and then this becomes lambda e. All right, so now you see that, okay, so what I'm going to get is this. Ke d squared plus r squared, and then 3/2, right? So dq equals that. So now you can even take out this lambda e, right? So it's going to become, so first you get lambda e dl, that's dq, right? And then you can write it. You can take out even this lambda, right? So you still get Ke d over d squared plus r squared to the power of 3/2. Now lambda e, take it out. You have integral dl. And this is actually a very easy one because you don't have any function here, right? You don't have any function. That means you're just integrating this dl itself. What do you get? You're just adding all these little lengths together, right? Remember, this is just going to become, I'm going to write it here. This is just, you just add all these dl's together, right? No, let's use li. Right? So you're going to break it into an infinite number of pieces. Each piece has a length, okay? And then if you add the length together, all the lengths together, what do you get? You just get the whole length, right? You just get the whole length, right? So this is just going to be, so you see that I don't even need to use any integral table because I don't have any function here, right? If you don't have any function here, you're just adding this little variable together, okay? So you just get d squared times big L, right? Because the integral is just going to give you a big L. And then lambda e times big L, that's the definition of this, right? Because I know that lambda e equals q over big L. And lambda e times big L is just going to give you the total charge, right? So at the end, the final answer is going to be very easy. You see that I didn't actually really use the integral table, right? Because I don't have any function to integrate at the end. So I only get Ke d big Q over d squared plus r squared to the power of 3/2, right? And that's it. That's my final answer, right? Direction, still in that direction. So if you want me to draw that for you, I would say I would draw an arrow in that way. That's the direction of the electric field. It only has x component, right? And then magnitude is going to be that, right? So if you give me numbers, I can calculate these numbers for you. But this is going to be a general conclusion, okay? It has d and the charge q of that's the total charge of the ring. Of course, you need the total charge of the ring to calculate the number, and also the radius of the ring r to calculate the number. But that's it, right? Okay. So actually, you can even do that right here. Okay. So you see that if you don't write this dq, okay. Remember, as I said, when you integrate only this variable, okay, this very small piece with no function here, it's just the sum of this little length, right? So instead of writing this dq as this, right? Take a look at here. Now you're integrating dq, no function here. That means, again, this guy is just going to be equal to, you add all these charges together, right? So you're going to pick small pieces of infinitesimal charge, and then you just add all these little q's together. When you add all these little q's together, you're adding all these small charges together. What do you get? You just get the total charge, right? So if there's no function in this integral, that's even easy, right? So I know that when I integrate this dq, so I'm just adding all these small, infinite small charges together, no function, right? So I'm just going to get the total charge of this ring, which is just going to be big Q, right? So if you understand what this means, you don't even need to write the dq in terms of lambda e times dl. You will get the answer very easy. Okay, so that's what I said. The ring actually is it's actually easier than the rod because again the symmetry, and we have more constant in this ring. Okay, and then another way to check, one way to check if this answer makes sense is this. Again, let's take a limit. Let's assume that the point P is very, very far away from the ring, okay? So that means the ring's here, and the point P is gonna be, you know, in the other room, okay? Or even like 1 mile away from the ring. So in that case, what will this expression become? So now we're taking the limit when D is much, much greater than R, right? That's how we write it and mathematically, instead of using words. That means, now let's take a look at this equation. So the electric field in X component is going to become, okay, so big D is much than big, no, little D is much bigger than this big R, so that means you add these two guys together. This is negligible. You don't need to worry about that, right? You add 1,000 square plus 1 square. You don't need to worry about that. So this is going to be very close to Ke dq over d squared to the power of 3/2. Right? And this is just going to be equal to d to the cube at the bottom. Right? And if you have d cubed at the bottom, it's just going to cancel 1 power of this. So you just get Ke q over d squared. Okay, what does this mean? That means when you're very far away from the ring, look at this. This is the equation actually for a point charge, right? A point charge, the electric field is Ke times the charge divided by the distance square, okay? When you're really far away from the ring, the electric field at that point is the same as if all these charges, not on the ring, but just at the center. Does it make sense? Sure it does, right? When you're really far away from the ring, you look at the ring, it looks like a point to you, right? You can't even see, you can't even tell the size of the ring, right? So this does make sense. So that's one way to check if this answer makes sense, right? Because if the point P is very, very far from the ring, the effect of the ring at that point should be the same as a point charge right at the center, right? Because if the point P is very, very far from the ring, it doesn't really see any difference, right? It doesn't really see any the effect caused by the shape of this ring. All right? So this is the limit. This is an extreme case. All right? So we have finished the rod and the ring, okay, one-dimensional object. That's the only objects we're learning in this class. So we're not going to go to 2 dimensions, okay, do the duration for 2 dimensions. We're still going to use the conclusions. But the theory, okay, the math, the duration, I want you to know is the one-dimensional object, okay? Now let's take a look at the next question, a disk. Okay, so we're not going to derive that because we have already done a lot of derivation, okay? So what I'm going to do is that I'm just going to present a conclusion because the conclusion is very useful, okay? I can tell you the idea, okay? The idea is this. So if there's a disk instead of a ring, okay, you have a disk, and the disk is charged uniformly with a lot of charge, okay? So now there's a disk, okay, solid, okay, not a ring. And then I want to find the electric field D, okay, that has a distance D from the center of the disk. So you can still derive that, okay? You're gonna do some calculus, okay? So at the end, so the idea is this. I can tell you the idea, but I'm not going to do that here because we have already done a lot of derivation. I don't want you to hate me too much. So the idea is this. You imagine this guy is made of an infinite number of small rings, okay? So it's going to be made of one ring, two of them, three of them, right? See that? Okay? So the idea is that you think of this guy as an infinite of concentric rings with different radius, okay? And then you can use this conclusion for a ring and then make the R a variable, right? Because I said, you imagine this guy is made of rings with different radii. You make this R a variable, so you're going to integrate that variable, radius, whatever you call it, dr or something. You're going to find an integral with respect to this dr, and then you're going to use the integral table to integrate that function. Okay, so in that case, you will have a function, and then dr, you integrate that. Okay, but we're not going to do that here because it's too complicated. So the idea is that, okay, and then the direction, of course, from the symmetry, right? We already done the many times. The electric field is going to be totally in x direction, for sure, because each ring is going to only have a component in x direction, right? You add the electric field from each ring together, you will still get a vector in that direction, right? Because each ring, so all these electric fields, they are in the same direction. You can literally add them, okay? And then once you have done the math, okay, the integral, you will get this electric field created by this guy, okay? So it's gonna be a long equation, so it's on this slide, okay? It's gonna be 2 pi Ke times sigma E, which is the surface charge density, right? You do the total charge of this guy divided by the area of this guy. If this is a disk, then the area is going to be pi r squared, right? Because it's a circle. And then times this thing, 1 minus, okay, d. Okay, so this is the in x direction, right? And what we usually do is this, okay? Again, you don't need to memorize this. You don't need to memorize this, okay? We can make use of this epsilon. If you still remember, there's two ways to write Coulomb's law, right? Because Ke equals that. So you can replace Ke with this, right? Replace Ke with this, you will get a different expression, a little bit different. It's going to be sigma E over 2 epsilon naught, right? If you plug in, you get this. And the sigma E is still here, right? It's going to be a little bit easier than that. That's the only point. We use this epsilon naught. Okay? And then, okay? And of course, the sigma E is the Q over area. If the disk is very large, and that's going to be a very, very useful for us, very, very useful conclusion for us. If the disk is very, very large, right, very big, and you're only interested in an electric field very close to the disk, okay? So even if the disk is not very large, right, it's like this big, but I'm only interested in the electric field very, very close to it, right? So you take the limit when the big R is much, much greater than little d, right, for the disk, okay? You're going to see this electric field is going to become very, very easy. Okay? So this is going to be almost, so okay, big R is much greater than D, so this is just going to become R squared at the bottom, R squared square root. So you're going to get an R at the bottom. And D over R, again, big R is much greater than D, right? So this term is going to be almost 0, right? Because you have a very small number at the top, very big number at the bottom. So you're just going to get 1 minus 0. So that's just 1. And that's just going to be this, right? So that's going to be a very useful conclusion. When the disk is very big, the electric field created by this disk at a point very close to the disk, okay, it's going to be actually constant. It doesn't even depend on where the point is, okay? So it's just going to be the sigma E. If this is uniform charge, it's just going to be the electric field created, electric charge divided by area divided by this constant, okay? Why is this very useful, okay? Because now what we're going to do is this. We can use this conclusion to make a very uniform electric field, right? Because as I just said, if the electric field, you use a very big disk, okay? Use a very big disk, okay? And then this guy has been charged positively. If you are only interested in the electric field, okay, like close to the center and also very close to the disk, the electric field here is going to be in that direction, right? And the magnitude is going to be this, constant, okay? So then if you pick a point here, it's going to be the same. So in this region, if it's a point very close to it and then you are only interested in the region in the center, the electric field is going to be almost uniform, right? Almost constant. And we like uniform, constant electric field, right? Because that's easy, right? If I want to do calculations, calculate force or anything, right? Using that electric field, that's going to be easy, right? I don't want to use a crazy electric field. I don't want to calculate forces and motion of electric charges from in a very complicated electric field, right? I want everything to be easy, right? So, and then if you do the same thing, and then you place a negative plate very close to it, and then you charge it with the same amount of charge but negative sign, okay, opposite signs, okay. So the electric field created by this guy, okay, it's gonna be toward it, right? Because this is a negative charge, right? So let's say it's going to be E1 created by this plate, okay? Now this plate is also going to create its own electric field, but this plate creates the electric field in the same direction, E2, right? In the same region. So these two electric fields, they're going to add, right? Because they are in the same direction, they are all in the same direction. So if I put these two disks or these two plates together, and I'm only interested in the electric field between them, right? They are very close, so the distance between them is much smaller than their own size. If I'm only interested in the electric field between these two plates, the electric field is going to be very uniform, right? In the same direction, always has the same magnitude. What is going to be the electric field between them? Well, that's going to be E1 plus E2, right? So E1 is going to be sigma E over 2 epsilon naught. E2, if I charge them with the same amount of charge, okay, this is positive Q, this is negative Q, and they say have the same area. So they will have the same charge density, surface charge density, right? So sigma E over 2 epsilon naught. Okay, so you add them together because they're in the same direction. You can literally add these two numbers together. You would just get sigma E over epsilon naught. Okay, so that's the electric field between two plates. If you charge them with the same amount of charge but opposite signs, okay, the electric field between these two plates, if you put them very close, it's going to be very uniform, and then the magnitude is going to be this. So we make these things, okay, we call them parallel plate capacitors, okay. That's how we create uniform electric field in real life. So that's why I said this conclusion is very useful. Even though we didn't derive that, it's going to be very useful. Why are we interested in parallel plate capacitors? As I said, if I want to create electric field to study the behavior of elementary particles, right? Of course, I want to set up an easy electric field, right? Because the behavior of elementary particles, they are already very complicated. And then I put these particles in an electric field and study their behavior. Of course, I want to set up an easy electric field, right? I don't want to set up a crazy electric field, right? To make my life even harder, right? And then if I'm a physicist, I set up the experiment myself. Of course, I want to set up an easy electric field. And how do I set up an easy electric field? You don't get uniform electric field in nature, right? So you have to figure out a way to set up, make a uniform electric field in real life. And then you can use that to study elementary particles, right? And this is what we do for real. You just make two plates, okay? They don't even need to be very big, as long as you pick them, put them very close to each other, right? So it satisfies this condition. The size of each plate, it's going to be much, much greater than the distance between them. So the electric field between them is going to be very, very uniform, okay? And they're called parallel plate capacitors, okay? We're going to study capacitors in detail later, okay? But this is how we create uniform electric field in real life, and we do like uniform electric field, right? It's easy. Okay, so take a look at the electric field on slide 12, okay? That's how you set up. So, of course, on the edges, the electric field is going to be still like not that uniform. But again, if I want to make use of this electric field, I just make sure that the elementary particles, they're just around the center, right? They're just moving near the center of this electric field, these plates, okay? So the electric field is going to be this, okay? If it's a parallel plate capacitors, right? This is for a single disk, okay? So don't get them confused. A lot of people, they get them confused. This is for a single disk. And then when the disk is much, much bigger, okay, then the distance from the point to the disk, okay? There's a 2 here. But if you have 2 plates together, okay, you need to add these 2 fields, right, created by each plate. Then that's going to get rid of this 2. So if you use this equation, you have already, like this equation, by deriving this equation, we have already considered the fact there are 2 plates. So when you use this equation, especially when you calculate this sigma E, right, the sigma E is going to be the charge divided by the area. You don't need, remember, see, what is this sigma E? Sigma E is the charge of each plate divided by the area of each plate. So you don't need to double anything or divide anything by 2 when you use this equation, okay? This equation already has been derived, okay, using the fact that there are 2 plates, okay? So when you use this equation, when you calculate this sigma E and plug it in, this is just for 1 plate, okay? The amount of charge on 1 plate, the area of 1 plate. You don't need to double anything, you don't need to divide anything by 2, right? Of course, they will carry, you need to make sure they carry the same amount of charge to make this uniform electric field, okay? So this is the uniform electric field. And then why is this useful? We're going to take a look at it next time, right?